The learning objectives of this chapter are to know the Ecdis configuration on a vessel and carriage requirements. These training modules are designed to teach navigating officers the generic principles and operational use of electronic charts on an Ecdis. When all CBTs and the Ecdis workbook are completed, both generic knowledge and equipment-specific training has been achieved. The objective of the training is to enable Ecdis to be used in a safe and competent manner. The acronym stands for Electronic Chart Display and Information System. From 2002, an approved Ecdis system complies with the Safety of Life at Sea Chapter 5 Regulation 27 requirement to carry adequate, up-to-date charts. Information can be fed into an Ecdis system from several different sources. Click on each button in turn for further information. The primary use of Ecdis is to store electronic charts on which the ship's position is displayed. Some Ecdis devices can also store and display digital publications such as pilot books, list of lights, and list of radio signals. Some Ecdis devices are also capable of displaying information from the vessel's machinery, such as main engine, rudder, and thruster. Some Ecdis devices are also capable of displaying information from the vessel's machinery, such as main engine, rudder. An Ecdis could have numerous other connections allowing inputs from several other devices, such as an anemometer, echo sounder, and AIS receiver. In 2002, a revision to the existing regulations stated that an approved Ecdis device is acceptable under SOLAS Chapter 5 Regulation 19 for the chart carriage requirements. This means an Ecdis must be capable of storing electronic charts that are equivalent to full folios of paper charts for the intended voyage. Many years ago, various types of electronic charts were made to assist plotting and recording of large amounts of data. These were often associated with specialized operations, such as oil and gas exploration. Charts were viewed on devices called chart plotters or electronic chart systems. The chart plotter, or ECS, still exists today and is used on many types of vessels. It should, however, not be mistaken for a fully type-approved Ecdis. Merchant vessels started using electronic chart systems in the 1970s, causing a demand for worldwide electronic chart coverage. When an approved Ecdis system is carried, it can become the primary means of navigation, with a reduction in the number of paper charts carried. There are variations around the world with respect to carriage requirements. It is recommended to consult the flag state where the vessel is registered for advice. Some Ecdis systems are referred to as dual-fuel systems that can display various types of electronic charts. These systems, with backup and flag state approval, can become the primary means of navigation, removing totally the need to carry paper charts. From 2012 onwards, there is a rolling program to have new and existing vessels compulsorily fitted with Ecdis, which is called Ecdis Mandation. New high-speed craft from the 1st of July 2008 were required to have Ecdis. The illustration shows the rolling program for other vessels. Ecdis manufacturers get product approval under standards laid down by the International Hydrographic Office, focusing on the hydrographic elements, and the International Maritime Organization, focusing on the functionality of Ecdis. IMO introduced revisions to the standards when there are increased or changed requirements. When manufacturers follow the same standard, operators should find it easier to use different makes of Ecdis. Some advantages of Ecdis include the following. It is capable of displaying lots of information, recording voyage data. It has tremendous flexibility when it comes to file handling. It is space-saving compared to storing folios of paper charts, and saves lots of time chart correcting. A major disadvantage of Ecdis is the operator becoming fixated with the display, thinking everything they see is correct, and not maintaining other watch-keeping duties to support the navigation. Other disadvantages include: the software can be complicated to use. The chart display size is limited by the size of viewing monitor fitted, and when compared to a paper chart, it can appear small. The system can be prone to vibration damage, and most importantly, the operator can go into information overload, making it difficult to see what is important. The display size can affect the operator's situation awareness, particularly on a fast-moving vessel. When on passage at high speed, the small amount of chart displayed on the monitor means the operator may not be aware till it is too late of dangerously close objects ahead of the vessel. Under STCW 95 requirements, Table A2/1, a navigating officer is required to have a thorough knowledge of and ability to use navigational charts and publications such as sailing directions, tide tables, notices to mariners, navigational warnings, and ship routing information. The 2010 Manila Amendments make it mandatory for all navigating officers to be competent in the use of Ecdis to maintain the safety of navigation. There are additional duties for masters and chief officers to manage Ecdis. The presence of Ecdis does not relieve the watchkeeping officer from their normal watchkeeping duties to maintain the safety of the vessel. If navigation is totally or partly performed on Ecdis, there has to be an independent backup system available. There are two main reasons for this. Click on the buttons for more information. The backup should provide for safe navigation for the remaining part of the voyage. It should be capable of geographic representation, with route monitoring and voyage data recording as the main Ecdis would. If the Ecdis fails, IMO require the backup to be instantly available to ensure that failure does not result in a critical situation. It is recommended that the Ecdis software is backed up on an external device to enable a full system reboot if necessary. Loaded charts are already backed up on the supply disks. The Ecdis has to be independently connected to the emergency power supply in case of mains power failure. It should continue operating normally for at least 45 seconds to allow an uninterrupted switchover to emergency power. Let's summarize what you have learned in this chapter. An Ecdis displays other information apart from electronic charts. It's acceptable. And finally, that the main Ecdis should be backed up with a second. Let's summarize what you have learned in this chapter. An Ecdis displays other information apart from electronic charts. It's acceptable under SOLAS chart carriage requirements. We've learnt that an ECS is not an approved Ecdis. An Ecdis will be mandatory on a lot of vessels soon. Also, Ecdis is approved in accordance with IMO and IHO standards. And finally, that the main Ecdis should be backed up with a secondary device. The learning objective of this chapter is to know the devices connected to Ecdis. The Ethernet LAN is a wired link between various devices connected to the Ecdis. It is important that the physical connections are secure and the connecting cable is not damaged. Some LAN cables are fiber optic and damage if bent. Devices communicate around the LAN at a baud rate that represents the data flow in pulses per second. If the baud rate is set incorrectly, the device cannot communicate, resulting in lost information. Standard 61162, developed by the International Electrotechnical Committee, applies to serial line communication. IMO require a basic minimum number of inputs to Ecdis. These consist of a navigation receiver, a gyro or electronic compass, and a speed and distance measuring device. There are other devices to assist navigation that could be connected to Ecdis. These consist of a radar, an anemometer, and an echo sounder. There could also be machinery information displayed on Ecdis, from the main engine, the rudder, or thrusters. One of the most important devices feeding the Ecdis is the navigation signal, that could be from a Navstar GPS, GLONASS, Galileo, or E-Loran receiver. The navigation signal allows position stability on the chart display and allows Ecdis to track the vessel in real time. A system with integrity has an integrated navigation receiver, INS, feeding the Ecdis. If the primary navigation receiver fails, Ecdis will default to a secondary receiver, if available, and connected. The illustration shows an alarm on switchover. However, some Ecdis systems switch without alarming. If the primary navigation receiver fails, with no secondary navigation system available, the Ecdis will go into DR mode, using course and speed through the water to update the charted position. Point B in the illustration is the DR position, which can be misleading to an operator, because the Ecdis is not aware of any effects of wind or tide. If it was aware, it would position the vessel more accurately at the estimated position, point C in the illustration. The operator should see the discrepancy by checking the vessel's position with other means. The satellite navigation signal feeding Ecdis has error, which is the sum of many errors in the system and receiver. An error budget summarizes these errors, but sometimes the errors add up to give a large figure. Sometimes they cancel each other out to give a small figure. A satellite receiver simplifies its indication of accuracy by showing an h-top figure. A value of 2 is a good fix. The higher the number, the less accurate the fix. An Ecdis may look for a secondary receiver if the h-top rises above a limiting figure set by the operator. A vessel is tied up on a berth with Ecdis positioning the vessel off the berth. This is precise but inaccurate, as the receiver consistently gives the same position with the same error. The second illustration shows precision and accuracy with the Ecdis repeatedly positioning the vessel on the berth correctly. A vessel is tied up on a berth with Ecdis positioning the vessel off the berth. This is precise but inaccurate, as the receiver consistently gives the same position with the same error. There is a process on the Ecdis called position filtering that imposes a small time delay to the displayed position of the vessel. The delay, that could be up to 15 seconds, stops the displayed position jumping with errors in the navigation signal. The position filter can lead to apparent overshoots on a fast-turning vessel, as the illustration shows. It looks like the vessel overshot the corner, but in reality she did not. The filter acts a bit like a DR system, this time using course and speed over the ground, predicting ahead where the vessel will be, but then looks at the incoming navigation signals to work out where the vessel actually is. With the vessel turning, it is difficult for the Ecdis to predict ahead accurately. A short time later, the Ecdis catches up with the actual position of the vessel, indicating she is on track. Remember, the navigational receiver also has a filter, so the incoming signal to the Ecdis is possibly further time delayed. Ecdis is a very useful device to assist the vessel's navigation. However, there should be continuous checks on the displayed position using independent sources of position information. The illustration shows how a bridge team were misled with an Ecdis in DR mode. Grounding resulted west of the channel. When the radar overlay function is selected, Ecdis superimposes on the chart display everything from the connected radar screen, showing it in a green shade. When the navigation signal is accurate, radar overlay coincides exactly with the charted position of land and navigation buoys. The illustration shows radar returns from buoys coinciding with their charted positions, identifying the radar returns and that they are in their correct positions. The small radar return ahead to port, not on top of a charted symbol, is a good indication of a possibly small moving target. The radar returns from buoys can be seen, but one of them does not coincide with its charted position. This could indicate a buoy out of position or a small target and a buoy missing. ARPA radar will transfer the radar return from a ship target, but then also show an acquired target with circle and vector. When there is radar heading marker misalignment or gyro error present, the radar overlay will be skewed, as the The AIS signal of a target is seen as a blue triangle and classed as sleeping until the operator activates it via the AIS menu. The illustration shows an active target with vector indicating a course and speed over the ground. When a target is dangerous to the vessel, the triangle and vector are red and flash to alert the Ecdis operator. Class B and VTS AIS targets can sometimes be deselected from showing on the Ecdis display. Let's summarize what you have learnt in this chapter. There are many devices feeding the Ecdis via a LAN, and that the navigation signal is a critical input to Ecdis and must be correct. We've learnt that the level of accuracy varies on the navigation signal and that we need to keep an eye on the H-stop. The position signals are filtered, and that the radar overlay is a useful feature to assist monitoring. The learning objective of this chapter is to know the construction of electronic charts. An electronic chart is any chart displayed on an electronic system and used for navigation. There are many examples on land, in the air, and at sea. On an approved Ecdis, the only chart allowed to be used is an official chart made to a standard approved by the International Hydrographic Office. Some hydrographic officers saw the opportunity to make electronic charts by scanning existing paper charts, calling them raster or facsimiles charts. Raster chart production seemed a quick solution to the demand for electronic charts because of the already existing global coverage of paper charts and the relative ease of scanning the chart. An important feature of paper charts is the scale of the chart. A scale of 1 to 4,000 would be a harbour chart, while 1 to 27 million is an ocean chart. The cartographer who made the paper chart added a level of detail to suit the chart scale. This factor is very important with electronic charts, because they are copies of paper charts. There are, however, some limitations to raster charts. They are not flexible, as there is only one file. They cannot be interrogated with a double click. Errors on the paper chart transfer to the raster chart, and adding chart corrections means a rescan of the corrected chart. Because of the limitations of raster charts, some hydrographic officers and private companies decided to make digital copies of charts using a different method. Based on original information, they created digital vector charts. Source data is the information from surveys carried out when the chart was originally made, which is often missing but sometimes not guaranteed to be correct. As a result, many vector charts are made from paper copies, which include any original errors or omissions. Using an existing paper chart, the digitizer traces over the coastline with the digitizing tool. A click on the tool records the position of the tool on the tablet, and hence the coastline. The whole coastline and position of any objects, such as buoys, can be copied and saved in this manner. In the illustration, the filing cabinet represents the computer hard drive used to store digitized vector information. The drawer of the filing cabinet represents the land folder. Inside the drawer there are subfolders with some of the stored detail. Nature of the land, coastal outline, position of buildings, names of settlements. In 1985, IMO requested that countries start producing electronic charts. They stipulated that a country had to be responsible for their own sea areas. Countries without a hydrographic office could authorize some other responsible office to complete the task for them. It is a slow but ongoing process to digitize the world's folio of paper charts into vector charts. The chart digitizing process creates many folders with stored information. The files, when grouped, are called an electronic navigation chart dataset. Making vector charts involves recording lots of different information. The illustration shows a small amount of what is needed to create land detail in the ENC dataset. Digitizing a buoy for a vector chart also involves lots of recorded detail. Digital chart is a term relating to any type of electronic chart and could be raster or vector. One very important thing to remember is that digitized charts are generally no more accurate than the paper version of the chart. One exception to this, however, is the Australian vector chart series of the Great Barrier Reef, where more accurate sounding information is used from new data. Let's summarize what you have learnt in this chapter. There are various types of electronic charts with different formats. The common types are raster and digital vector charts. There are over 40 countries producing electronic charts. We've learnt that electronic navigation charts are the official ones to use, and that digitized paper charts are no more accurate than the paper version. The learning objectives of this chapter are to know about datums, the two types of charts and their use. The surface of the world is very uneven, with mountains and deep ocean floors, but is similar in shape to a squashed sphere, and can be represented by a surface called the geoid. The outline of the geoid forms what is called the meridian ellipse, with dimensions as shown in the illustration. When this ellipse is rotated about the polar axis, a spheroid is formed representing the shape of the Earth and is called the WGS-84 spheroid. This spheroid has become the datum for marine navigation and chart production in the world. All positions are on this datum. A vessel is alongside a berth when two fixes are taken, at the same time, from two navigational receivers set on different datums. Chart 1 fix puts the vessel in the correct position on the berth, indicating the chart and receiver datums are the same. Chart 2 fix puts the vessel in the wrong position, showing the mismatch of datums. Some digital charts have different datums compared to WGS-84. The chart indicates offsets that are simply corrections to be applied to a WGS-84 latitude and longitude to enable it to be plotted. A modern Ecdis will produce an alarm if there is a mismatch between the chart and navigation signal datum. The GPS receiver shows height above or below the WGS-84 datum, which approximates to mean sea level around the world. Electronic charts can show land heights above mean high water springs and water depths below lowest astronomical tide. There are also charts where the height and depth datums could be as shown in the text. A check on the chart legend reveals the datum. Some advantages of raster charts are that they are simple to make and a full-color reproduction of the paper chart. With WGS-84 datum, they are compatible with satellite positions. Mariners recognize symbols from the paper charts. They are approved for use on Ecdis when no vector chart is available. They often have the same name and number as a paper chart, and that correcting them is fast compared to paper charts. Some disadvantages of raster charts are: chart has no intelligence and cannot be interrogated for information. On zoom it becomes distorted. On zooming out, the whole chart with borders will be seen. Cannot be used to predict groundings. They need large amounts of computer memory. Small screen display shows a little bit of chart. Raster charts are obtained from official chart suppliers in the same way that paper charts are, arriving on board the vessel as a set of disks for loading onto the Ecdis computer. There are many charts on the disks, but usable charts are those that have a permit or license for the Ecdis. Click on the button to get more information on raster charts. These websites give information on raster charts. This text from IMO describes a vector chart for use on Ecdis with reference to IHO standard S57 for electronic chart production. A vector chart produced by a country's hydrographic office under S57 standard is called an official ENC. The first two letters of an official ENC chart name identifies the country of manufacture. Private companies realized it would be a long time for hydrographic officers to chart the world digitally, so they decided to make their own versions of digital vector charts. They are classed as unofficial because they are not made by a country's hydrographic office, but are commonly found on vessels. Ecdis will warn the operator if the next chart is unofficial. The chart cell is given an 8-character identifying code. Mouse over the chart numbers for more details of the code. The usage codes gives an indication of where each chart should be used. The scale of the vector chart is consistent with standard radar ranges, enabling the radar overlay function to work correctly on the Ecdis. If the scales did not match, the radar overlay would not coincide with charted objects. A vector chart has a compilation or digitizing scale the same as the original paper chart, making the level of detail the same. If a general chart at small scale is zoomed in, there will be a low level of detail that would not be acceptable at the larger scale. This means a vessel must have a variety of chart usage types to cover the voyage, from harbour plans to ocean charts. Some advantages of vector charts are that the chart has intelligence and can be interrogated for information. The Ecdis using these charts can predict grounding. The chart allows route validation, as seen in the second CBT. There is a seamless chart display on the Ecdis screen. The charts can be corrected more quickly than paper charts. They are approved for use on Ecdis, compatible with WGS 84 positions. Some disadvantages of vector charts are that they can be more complicated to use compared to paper charts. The operators can become fixated on the display, believing it to be always correct. A small screen can only show a limited section of the chart. The operators need confidence and skill with computers to confidently use them. Creating them is a time-consuming process. Let's summarize what you have learnt in this chapter. The WGS 84 datum is the standard navigation datum for Ecdis and ENCs, and that height datums vary from LAT to MHWS. Make sure you consult the chart in use. We've learnt that the official ENCs originate from the country's hydrographic officers, that there are unofficial vector charts in use at sea, that ENC usage code 6 is a berthing chart and code 1 is an ocean chart, that the chart compilation scale is very important, and that there are advantages and disadvantages with all chart types. The main learning objective of this chapter is to know the supply of and how to recognize official vector charts displayed on an Ecdis. The S57 standard informs official ENC chart manufacturers there should be up to 220 objects in the chart dataset and 200 attributes associated with objects. An attribute is how the object will be handled by the Ecdis software on the chart display. The attribute SCARMIN dictates at what minimum scale an object will be visible on the chart display. When the scale value is exceeded, the object is removed from the display. If the SCARMIN attributes are not effective, the chart display can become too cluttered with unreadable information at small scales. The International Hydrographic Office set up a committee called WEND for the coordination of chart production and chart supply around the world. The WEND committee has a supervisory and advisory function with three main principles: that the organization responsible for surveying an area should also be responsible for chart production, that chart data must comply with requirements of IHO and IMO standards, and that a quality assured system has to apply to data production. WEN system led to the creation of regional ENC coordination centres, whose main function is to collate charts from a country's hydrographic office and organise their distribution via authorised service providers, often called value-added retailers. Some countries distribute their own vector charts direct from their hydrographic office, for example Japan and Australia. RENCs have several functions apart from collating and distributing vector charts. These are issuing of chart license or permit, ensuring ENC chart data is consistent, encrypting chart files for data protection and anti-piracy, controlling updates. The UK Hydrographic Office supplies charts and has grouped them into 3 folios to make selection easier. Click the buttons to see the folios. This consists mainly of ocean and general bands 1 and 2. This consists mainly of coastal and approach bands 3 and 4. This consists mainly of port and berthing charts bands 5 and 6. The chart installation disks contain other files apart from the chart dataset. One very important file is the README file that has lots of information concerning charts and Ecdis in general. The README file can be seen on the UKHO website. It is recommended when loading new versions of a chart or updates that old files are deleted, as some Ecdis devices will display the original file rather than a newer version. When creating electronic charts on Ecdis, manufacturers apply the S57 standard differently, causing slight variations in how images of an object look on the chart display. In the illustration, one manufacturer looked at a beacon and coded it with a top mark. The other manufacturer saw it as a day mark. When the ENC dataset is loaded onto the Ecdis, there is a conversion process, creating what is called a System Electronic Navigational Chart, enabling the Ecdis to show chart information. Each Ecdis converts the ENC dataset in its own way, resulting in small variations in how each make of Ecdis displays chart information. Some value-added retailers convert the ENC dataset into an SENC before delivery to the vessel, which speeds up the process of loading charts on the Ecdis. Ecdis software includes a file called the Presentation Library, which allows the Ecdis to recognize symbols in the SENC and draw them on the chart display. If the Presentation Library version is out of date, Ecdis will not recognize objects in the SENC and cannot display them, making the Ecdis not comply with SOLAS carriage requirements. When the presentation library is out of date, a magenta-colored question mark appears on the display. A large one indicating no knowledge of the object, a small one indicating no knowledge of an attribute. Let's summarize what you have learnt in this chapter. That S57 is the IHO standard for vector charts, and that an object's attribute influences the managing of the object on Ecdis. We've learnt that WEN is the IHO's umbrella on world chart production, and that there are 2 RENCs in charge of chart coordination and distribution. That the ENC dataset converts to an SENC when loaded on Ecdis, and finally, that the Ecdis presentation library needs to be the latest version to display objects correctly.